Hello. So previously we have introduced the very famous DQN algorithm in reinforcement learning. So today let's use another video to further discuss some technical details or some intuitions behind this algorithm. Okay. So let's take a step back, and we know that reinforcement learning algorithms, they essentially solve the problem that what is the best way to act if an agent doesn't know what is correct, and the agent only has a scalar reward of how well this agent has done so far, right? So that this green paragraph here essentially stated the basic situation or the basic problem in reinforcement learning, right? So normally, how do we approach this problem? So the reinforcement learning algorithms, they utilize the temporal difference learning. Okay, so basically the algorithms, they try to learn some patterns or some structures between different stages, or essentially is trying to capture the, as we mentioned before, the dynamics or the transitions between each time stages, right? So, and try to have the maximum return. So essentially the algorithms, they try to make the predictions as the best as they could based on the previous experience, right? And here in the red, we say that the reinforcement learning agents, they simply try to maximize the sum of the future discounted rewards and using the discounted factor gamma, right, as we mentioned before. And this discounted future reward, and that is simply called return. Okay, so specifically in the DQN that we discussed last time, so we have something called experience replay. Okay, so this experience replay, this experience ET is a tuple including the current state ST, the action AT. So here we use A instead of U. So this A is the action. So action AT, and the reward for time T, and the transition, not the transition, the next state, ST plus 1. So here, essentially, this temporal or this experience, this structure, this tuple here, it captures sort of the some experience, right? So from this tuple here, the agent could observe the next state generated by the previous state and the previous action, right? So, and of course, the reward from the previous action. So this intertemporal tuple or this pair here, it is actually very helpful for us to construct the loss that we're going to use to update the parameters in the network. Okay, good. So, and this will be a way, as we mentioned, to model the transitions, right? Because those will be not directly observed by the agent. Okay, so good. So specifically, in the algorithm in DQN, so we can sample a batch or mini batch of such experiences for each sample. Okay, so first we feed this current state ST into the network and to get this Q value. Okay, so given the input of S, A, and with primary theta. Okay, so and then we feed SP plus 1 into the network, and to get this another Q value, but that would be taking S prime, the next state, A prime, the next action, and theta, okay, and the network parameter, okay. And then we choose the maximum, so by choosing some action to maximize this Q value, okay, for taking the next state and next action, and we set this target value of the network to be this value here. So it'll be the gamma, the discounted future reward, but which is the maximized by taking some action A, which is the maximum of the Q value, okay, using parameter theta, but it should be theta fixing the parameters, okay, and taking the next state and next action, plus the current reward, RT. And this is set to be the target value of the network, okay? So here and then we could train the network with the current state ST as the input to update the theta. So how do we do that? So the output from the input of ST, so it'll be simply the Q, okay, with the current ST and AT. And the gradient descent, this part, so this simply minimizes the loss. And how do we obtain this loss? And that'll be just the squared. So that'll be maximizing the square as this the loss, right? So the loss would be the squared distance between the target value that we just defined and the Q value here, okay, with the input of ST. So, and here we need to note that this theta, we need to fix this theta, okay. All right, so here this loss will be just the, it should be the square square distance, right, between the label, which is the target Q, and the original Q as the output, okay. So how do we interpret this target label, and how do we technically to obtain this one, right? So intuitively, the reward, so here, okay, so this label or this gamma times maximize Q as prime A prime theta plus RT. So this term here, or this label, so essentially they're talking about, so in plain English, so it's saying that the reward, the agent or I just saw, okay, so which is RT, and plus gamma, the discount factor, times something else. So this would be the best prediction of the return, okay, of the future return, given that I take what I think would be the best action in the current state, okay. So here I'm trying to make the best prediction that I could, okay, using the experience, and follow the policy or this policy from then on, okay. So here essentially we're trying to make the prediction just one step ahead, okay, not too much, just one step ahead, and that'll be enough by definition of this label or this target value, okay. And technically what we're actually doing here to try to obtain this target Q, and we know that the neural network, it could simply outputs all the possible Q values given S prime and A prime, all those Q values over all the actions, okay. So we could, that'll be, and then it'll be very easy for us to find the maximum value of this Q by choosing some A prime, by choosing some A, okay. All right, so this will be sufficient to obtain this this target Q value, and then using this value, and then we're able to derive this loss, and then update the parameter of this network. Okay, good. So here, the most important part again will be this experience replay, right? So from this ET, from this experience, we have some kind of this relation or those experience or this knowledge that the agent have accumulated from the past, right? So this agent could try to make some prediction based on the current state ST and AT. Then this agent will know that this given st and at, then the state becomes st plus 1 with a high probability. Then the this will be useful for us to input to the Q function to obtain the maximum of the Q values by simply looking up all those possible values of A to try to maximize the Q in the one-step future, right? Okay, good. So that'll be a useful discussion on this DQN and the corresponding the loss function and the mechanism or the intentions behind that. Okay, hope this will be useful. Good.